Live now, sir. So, hey
Hey, good
guys.
afternoon, Vikas.
Yes, sir. Good afternoon. It's an honor for me to have you in my series of webinars that we'll be doing. This is called as TensorFlow Thursdays from TFUG Bangalore, TensorFlow User Group Bangalore. This is one of the meetup group where we actually wanted to just give and community back with something on technology. Thus, we just focused on it and we just got it back for the world so that we can focus on other topics also. I think it's an immense pleasure for me to hosting you in this event because I saw your TinyML talk and I told, okay, edge computing can be the new thing. So, giving about the brief insights about Amit Mate sir, he is the CEO of Gmax. This is a company which is focusing more towards the edge computing aspects of deep learning, where we have to still learn what is the actual aspects that we need to cover and what is the actual requirement for edge computing to be accelerated. Of course, there are TPU cards which are really available, the Coral boards, but if it's not available, if you want to really give a very cheap approach for a novel approach for your project, I think this session is for you. So I welcome Amit Mate sir for this series of TFUG, which is called as TensorFlow User Bangalore, which is called as TensorFlow Thursdays. And thank you so much for accepting at a very short notice, sir.
Hey, Vishwas, thanks and thanks for the kind introduction. I would like to welcome you all. And it's an honor to be here and to be talking with Vishwas about a topic that we both care about. Uh,
Yeah,
guys, Vishwas, should we just go ahead in the presentation or,
sure, sir. I think
Yep.
you can
Okay.
give an brief intro about your industrial journey so that they can get to know, okay, what was the thing which really got evolved throughout this process, and what is his experience throughout. That means your experience in working on Edge, so that they can get an insights about how this industry has also evolved through your experience also.
Sure, sure. No, great. I think that's a great way to start that. So I'll briefly tell about myself. My name is Amit. I am the founder CEO of Gmax Intelligence, and we are an AI/ML software company. We build AI/ML software that enhances the safety and security of people and assets. And so basically, what we do is real-time visual AI use cases like people, vehicle, activity recognition. And so how are we different? We are basically doing all the AML processing on the edge itself, on the edge compute, right? And that's a very challenging area because there's constrained memory, compute, storage. And so how do we adapt AI/ML to run real time on edge is basically what we do as a company. And then I'll also throw light upon how did we reach this point and what are we going to do going forward, right? Regarding the history, right? So I was an engineering manager with Qualcomm Research and Nokia Research. I have 20 plus years of experience in the industry, and I started off my career with Nokia Research in Helsinki, Finland. Then I did a startup in Silicon Valley. Then I moved to East Coast. I did another startup there. Then moved to Qualcomm, spent a decade, and then moved back to India through same Qualcomm Research and. That's when I got introduced to AI. This was around 2013. So we launched India's first multi-script OCR engine right on the edge device, the smartphone, and so it could do multiple languages like Kannada, Telugu, Tamil, Devanagari, of course, married it with English, and there's like a complete OCR engine right there on which could work on your phone of those days, right? Those were like dual core days, early quad core days, and we learned a lot about how to accelerate these workloads even without the deep learning models, because 2013 2014 you didn't have a lot of deep learning models. Like the TensorFlow Lite equivalent wasn't there on the phones, right? So we had to do our own software to accelerate those things. And so we learned a lot. I mean, we learned about business aspects, technical aspects, in my mind at least, that was the idea for Gmax, that you can't do one modality of AI, it has to be multiple to build a solution which is useful to end people, right? And so the focus what we have is obviously how can people use these things in their daily life, how to automate the drone, the boring tasks, right? So I think we started one by one. And so the way it started was during COVID. the community workers in my community, right, as well as in many other communities, I think usually they get paid based on biometrics or fingerprinting. So every day they come, they note their attendance based on fingerprinting, and they count as a day present. End of the month they get paid. But after COVID, no, nobody wanted to use that fingerprinting, and so they told me, how do we solve this problem? I said, okay, give me some time. I'll build a facial recognition attendance system entirely on the edge, and I put that, and then they said, okay, we have two gates now. These two need to talk. So we said, okay, we'll have to connect the two. So okay, we'll use 4G. 4G in, let's say, a machine-to-machine communication format, and we connected the two. There are a lot of challenges in terms of synchronizing, the AI, transfer the learning of one device to the other device. And then we also figured that, okay, now we have to connect them. We have a cloud component, which came out of necessity, by the way. We figured, okay, we might as well put some intelligence in the cloud. So that becomes like a networked intelligence model now, where, all these devices have intelligence, and there's intelligence in the cloud as well, and all of these can work together to give you like a very good experience, or a great product. Basically, that's the basis of it. And suddenly I found myself doing the same thing which I was doing years before, because my experience has been in building wireless base stations and wireless technology, where these multiple nodes kind of connect each other. But the focus was on the modem part, how these connect reliably. Now what we're doing is we are making them network over this network to exchange pieces of information, which makes the system more intelligent as a whole, right? So I think going back to the topic of today, right? So what we'll do, Vishwas, is we'll cover what is here in the agenda. I don't know if you can see this. Can you see
sir,
the?
I'll share the screen. I share the screen. Yeah, I think you can go for the presentation mode, and you can just move on.
Okay, all right, cool. Yeah, sure. So I think the crowd mostly knows about AI, ML, and DL, right? Artificial intelligence, machine learning, and deep learning. But we'll just cover it for the sake of completeness. We'll take a look at what people call as edge, and we'll take a look at what are today's DNN applications, right? How the applications that end users kind of experience and feel, they are not islands of ML or DL, right? There's a combination of everything. And we'll take a look at the application stack. And once we look at the stack, we'll kind of dive deeper into the stack and see really what these computations are and why do we need to accelerate these, right? Going to the presentation. So I think I thought it may be good to just give a introduction to what really is artificial intelligence. I think a lot of people intuitively know it, but I like this definition by Dr. Raj Reddy. He actually got his ACM award in artificial intelligence way back in '95, and he almost predicted the onset of let's say devices like Alexa, Kindle, and e-commerce and everything, right? And so he also said that when people will be able to do 1 billion computations in a second, it will manifest as intelligence, right? So that's from a compute point of view. But I think he has a very simple definition for saying what is artificial intelligence. He's saying, okay, if an act or a series of acts, if it accomplishes something which if a human does, and you call it intelligent, then it's machine intelligence, right? So let's say if you have a friend who is driving a car, and you would say, okay, the way he's driving a car is really intelligent, right? Because he's taking care of the traffic, and he's able to get to point A and B in spite of the traffic at a very reliably and safely and quickly, right? You would call that person as intelligent. Now, if that manifests as machine intelligence, where the machine is driving the car, then you would call it as intelligence. And so, as you see, I mean, these definitions change, right? Maybe a few decades ago, if you did, let's say, you multiplied two 10-digit numbers and you gave an answer, you would call that person very intelligent. But now everybody has a calculator, and so what is human intelligence kind of keeps changing. It's kind of a moving target, right? So out of that, I think this diagram which tells us that machine learning is a part of artificial intelligence, right? Where machine learning is really the ability to learn and execute. And execute means infer, right? The ability to execute without being explicitly programmed. And that's the reason why it's so popular, right? Because a lot of visual AI use cases or speech AI use cases, you can't explicitly program the corner cases. You need to come up with a model which kind of takes care of the inputs without explicitly programming, as long as they conform to a distribution. I mean, that's really the math behind deep learning, right? And or machine learning. And then within machine learning, you have brain inspired networks, right? You're spiking networks, and you got your artificial neural networks, the neuron based, the famous perceptron and the neuron, which we all have learned. And deep learning is nothing but a subset of that, where you actually have a combination of these things in a fashion that makes it a deep network. So Vishwas, do we stop for questions, or how does it go? I mean, should we just keep talking?
Sir, you can complete the session like in such a way that, okay, you complete everything. Like, people can ask doubts in the comment section, like, and we will take the questions so that
Okay.
all the concepts will be clear with them, or else if it's not clear, they can clarify it later.
Got it. Got it. Okay, wonderful. So I think we covered what was AI ML DL in some clarity. Now, what is edge, right? This is the most comprehensive definition of edge according to ARM. So edge comprises endpoints, smart nodes, and gateway. And endpoints are like microcontroller-based devices, right? Your M0, M1, M2. And so a lot of these devices like AR, VR goggles, or speech recognition modules or smart home endpoints, they have microcontrollers. The smart nodes are application processor based devices. So the same chipset that goes in a smartphone, right, that's going to drive a smart camera or a surveillance camera, small drones, small robots. And gateway are server class devices, right? So there's also a lot of edge compute coming along with the base stations these days, where what happens is, because of 5G, the round trip time between these endpoints, nodes, and gateways is so less that you can execute all your AI on the gateway, and on the node, you wouldn't know whether the AI was done locally or on the gateway. And that's the whole thing. That's how it differs from cloud, right? I mean, cloud, we know there are delays of tens or maybe hundreds of milliseconds where data flows to a cloud network and comes back to the result. But here it's almost real time on all those points, right? And so that's the definition of edge. So we looked at edge, we looked at AI, ML, and DL. Now I want to give a small demo of really how end-to-end DNN application looks like. Right? These are applications which people can use as, and these are actually built by Gmax, and we are commercializing many of these as a packaged product, right? So let's take a look at this.
Okay, now Lakshmi. Okay.
So as you notice, this is a facial recognition product. Then this is a product based on a face, but it is kind of mask recognition. Here we are doing activity recognition. Here it is number plate. Here this is monocular depth sensing. So using a smartphone camera, we actually figure out at every pixel what is the depth of that particular object which we are seeing. And so the redder the object, the closer it is to the camera. And this is really one of the ways you can actually use to maneuver robots as well, right? Or maybe self-driving cars. And down here we have a bipedal. Like if you see here behind this, there is a bipedal robot that is. So this is a bipedal robot that.
Okay, Chickalakshmi.
That is scanning the ground to figure out the unevenness of the ground, and then accordingly it is operating its motor. So this is also deep neural network based, and we kind of trained this model in a simulated space from scratch and made the robot to walk in that space. And this is a hand detector, a very accurate hand detector, which you can use in VR and other gaming things, right? So as you see, I think the point I want to make here is that in every application, be it facial recognition or number plate, there's not just one model. There are multiple models in place, right? Like in the car, you want to detect a car, a two-wheeler, three-wheeler, four-wheeler, and then you detect a plate, and then you do OCR, right? There are at least 3 models deployed. Here there is, again, facial and a bunch of other models, right? So I don't want to reveal all the details, but really the thing is, the more deep neural network models you run on these edge devices, the more intelligent your solution is going to become, right? So in facial recognition, if you want to marry mask and no mask detection, you need more intelligence. Then you may want to add some more modality to it to make it spoof free, right? Like if people are spoofing with, let's say, liveness, or rather with images, and then you want to detect whether it's live or not, they need more intelligence. So I think most of these solutions, what we think is, it's just the beginning of the Moore's law equivalent of edge AI, right? And we will see as the time progresses, more and more intelligence is going to get pushed to edge devices. And there's the equivalent metric what people call as picojoule per inference. So picojoule per inference basically gives you how much energy was needed to compute one inference on an edge device accurately, right? And so the more intelligence you need, you'll need to run more inferences. And the more power efficiently you do it, the more intelligence you'll be able to cram on your devices. And that's how, this is the beginning of the journey now. I mean, these are really, in 5 or 10 years, all these applications on a battery operated edge devices are going to look very toy like, right? So yeah, so I think the whole purpose of this demo was to show that, the deep neural network compute is going to stay there and it's going to just increase. And so we need to figure out a way to basically accelerate these applications so we can put more intelligence on the edge. So assuming there are no questions so far, we will continue. And so this is how a DNN application stack looks like, right? So most of us are actually familiar with this upper level stack, right? Where we actually have applications like vision, robotics, speech, and we map it to a deep neural network or a deep reinforcement learning network, which in turn uses a deep neural network, right? And so you do, architectural innovations, loss function innovations in data augmentations, and then you come up with a high level model like a Keras model or a PyTorch model, which you train. But then that's not in itself something that you can run on these edge devices, right? Or you have to convert it into what, the real-time format like TensorFlow Lite, or the equivalent from Qualcomm called as SNPE, and again PyTorch by Facebook. And what you see here is this is the real-time stack, right? And what you see at the bottom, this is the edge compute on which we accelerate all this, networks, right? So on the top you have this application level models, but then underneath this is what is giving you the accelerations. There is DSP or neural processing unit, the CPU, this GPU, and they all come in various packages, right? Like Qualcomm will have its own configuration of all these compute. NXP will have its own compute. And so as a application or a DNN or a AI software developer, you need to be aware, how do I get to the required level of intelligence? How do I accelerate by mapping the workloads to the correct? And then again, tying it together for a real-time experience for the end user, right? And so I think, yeah, so the main point here is that what we need to focus on from an acceleration perspective is what are the accelerators, and how do we actually or why do we need to accelerate, right? So what we'll do today is actually we'll focus on this this hardware, and we'll see what is really the bottleneck in these to do more computations, and how will this evolve in a way, right? And so this doesn't mean that this is the only way to accelerate the workload. I mean, a lot of innovations happen here. How you design your network. Do you really need 100 layers? Can you do it with 10 layers? How do you connect these 10 layers? Again, what kind of loss function do you use? Is it really so smart that your objective is achieved without needing a big network? I mean, these are all what researchers and practitioners kind of figure out, right? There are ways to do it, but we'll not talk about these today. Today's discussion is going to be focused on these hardware compute types, and really how this is evolving to basically give you the acceleration that is needed for today's applications. So let's take a step back and then see how do modern deep neural networks look like, right? I mean, most of them are like 5 to 1,000 layers. They are CNN based, and what we see is there is convolutional layer in the beginning, in the mid level, and at the end you have a fully connected layer, and which kind of spits out a probability of the object. I mean, this is a very simple model, but the depth sensing that I showed earlier will have a similar structure. or the robotics in the bipedal robot will also have a similar structure. It will have some layers of CNN, a fully connected layer, and then it'll have a regression kind of output which controls the motors, right? And so if you look deep inside the convolution layer, these are the layers which typically people use, right? And so all the modern networks which today we know work in the cloud, they have all these layers. And so what we need to do is, how do we make sure that once we bring them to edge, even with all these layers and computations, we're still able to do it in a tiny form factor and with less energy, right? I think that's the key. And okay, so let's go into the next one. So this is kind of another slide which shows really what is going in each of these networks, right? I mean, people are familiar with EliNet, AlexNet, VGG16. These are very popular and common networks from a few years ago, right? But they have kind of become standard, like things like ResNet 50. They are, the heart of most of the feature computations in many networks. And so if you break down the number of layers and the number of computations that happen, so this is the thing which stands out, right? The weights and the MAC operations. So most of these networks, the underlying computation is MAC. So this 3.9G tells you there are about 4 billion MAC operations needed to compute one inference for a ResNet 50. For Google EliNet, this is 1.5 billion, right? And the number of parameters is 25.5 million for ResNet 50. And this is 138 million for VGG16. So you may be using all these networks, but this is the amount of data for every inference this has to be deployed, right? Like 15.5 billion computations, 138 million parameters, and it gives you an output. And we are doing this, why? Because we think this is faster than doing a traditional way of explicit computing. So you can imagine that the challenge is immense, right? And so let's delve a little deeper into how we actually finish off, so that some of the networks which I showed you earlier were running at 10 frames per second, which means you could do 10 such computations within a second. So this kind of workload can be handled by today's edge compute in 100 milliseconds, right? And so it's a humongous and a momentous task. And let's see what else people do to speed it up, right? So so this is what happens under the hood, right? I think so. I've taken an example of a TI chip here, but this is just an open source chip, I think, and I mean open source material. But most of the other chipsets from Qualcomm and XP will have a similar format for TensorFlow, for SNP, for PyTorch, right? So what you do is, you have a high level model, you train that. Then there's a network translation tool, which is kind of aware of the underlying hardware, or in some cases, it even spits out a hardware agnostic, accelerated network. And then you have this runtime which interprets that and maps it to the actual hardware. And so this is really a format which is common across most edge compute today. And if you open up that chipset, which I just showed, right, this, Sitara, this TI chipset where this acceleration is happening, you will find that it has multiple cores, right? There's a DSP, there's an ARM, there's a GPU. So this is the same as the stack that I shared earlier, right? And so what really, people who are writing the firmware that is close to this network, the people who are actually translating the network and accelerating, they basically use this hardware and exploit the features to give you a real-time computation, right? For needed for these networks. So going to a level deeper. So if you look at the basic compute element, right, the ALU, and so that's what is shown here for a SIMD architecture, which is kind of most CPUs. And then this is the new architecture which is needed to speed up the the AI DL compute, so that we get this real-time performance, right? And so let's take a step back. I think we looked at the AlexNet table a few minutes back, and we saw that there are about 724 million MAC operations. MAC is like multiply and accumulate operations. And so for these, you need 3 billion DDR reads, right? Because each MAC operation is going to be one filter coefficient read, one input read, one partial sum read, and one partial sum write. And so if all of that data was in the DDR, you have like a 3 billion DDR read just for one inference. And so this table here shows you like how bad it is to get that that field or that specific parameter from the DDR, right? Because DDR or DRAM takes almost 200 times the energy as compared to if all those parameters were present locally in the compute elements, right? And so this is the hierarchy which shows that if all the data were in the register in the ALU, then it's almost the same energy cost as if you were computing locally. And then if you had to get that those parameters from a neighboring processing element, right? So you compute something here and you send it here so that you compute the MAC operation, which gives you the intermediate results for the network. Then you transfer it here. Then that requires twice as much energy, which you can imagine. I mean, if you had connected the network this way, then it has a few hops and a few cycles are needed to get to the point. And then if most of these computes come with a buffer, which is kind of a in the memory hierarchy where it is kind of sitting a little away from the all these compute elements, which requires 6 times according to this study here, which was done by MIT, right? And the DDR is the most expensive, where you need like 200 times the energy. And so if we were to do this on the SIMD architecture, you can instantly see that these operations can be 10 to 200 times slower, right? So we really need, like, what the inference which we were expecting to do in 100 milliseconds, it would probably take like a second, 2 seconds, and then you'll lose the real time aspect of building the application, right? So what we want to do is use SIMD architecture, not use the SIMD architecture, but use like this advanced architecture where all these elements are actually interconnected, and you can also multicast parameters into all these ALUs. And so this is really the new architecture which kind of came out of research first from some of the US universities, and then most of the chip vendors are adopting this kind of a architecture for their chips as well. So this is really showing you how a particular 1D convolution would be mapped on this kind of hardware, right? And why is it more efficient? So as you can see here, this is your typical 3x3 filter, and this is your 5x5 input feature map. And let's say you have to do a 1D convolution between this first row here and first row here, right? And so traditionally you would have to set up all these parameters separately in the memory, read it, do the dot products, then sum it one by one, and you can easily see that each of those MAC operations are going to cost you a lot. But when you map it to a data flow architecture like this, you can really exploit it by multicasting the parameters first, so you don't kind of bring the parameters again and again from the DDR. You can also transfer these intermediate results between this ALUs, so you can minimize again the reads and writes. And so in a nutshell, what we are doing with this architecture is minimizing the data movement within the compute, right? We are minimizing that. We are making the intermediate results, the weights, the feature maps available at the point where it's needed, right? And so that's really the new approach of computing this efficiently. And the similar can be applied to a 2D convolution. And so so I'll share the slides. You can take a look at this, and then you can see that if you have multiple processing elements, right, P1, P2, P3, you can break this CNN load, or this where you are actually multiplying a filter with the input map, and map it to those processing elements in a way that if you deploy all these processing elements at once, within a very few cycles, all those compute can be done and the result can be obtained. And really at a high level, this is what is happening inside, right? And so I think those of you who are inquisitive about it, you should kind of take paper and pen and do this math, and kind of convince yourself that, okay, this is how it works, and this is how you get these advantages, and that will work out, right? And so a lot of techniques are used in addition to these, right? So people use fixed point arithmetic. Floating point is more expensive, it's 32-bit, more operations. Fixed point gives you similar results without the extra, power. Then people also reduce the number of operations in the model size. So a lot of times, these heavy models, once you transfer to these accelerators, people use compressed models. They use just-in-time uncompressing. That's much faster than, let's say, transferring all those millions and millions of weights one by one and then figuring out, okay, most of them were zeros. Instead of that, you send a compressed model, do the uncompressing, and and so you can imagine that to do all of this, a lot of intelligence is required to map these networks to these compute elements right here on the this array of ALUs, right? And so that's what most people who are developing this accelerator, they do. They understand the underlying hardware, they understand the network structure, and they map such that they control the flow of variables and the intermediate results in a way that all of this can be achieved at a very high speed. So yeah, so I think that that really is what is driving a lot of the improvements in the edge computations that are available today. And as you see, since most of the computations are MAC operations, and DSPs have been naturally the target compute for MAC operations, you can see that these DSPs are coming back to the fore with some of these modifications to run edge compute load on the edge platforms, right? So yeah, so before we go into the backup, Vishwas, that's the main presentation I had. Yeah, so let me know if any questions from your side.
Yeah, I made some notes also. So guys, don't worry. Even if you don't understand anything here, I'll be giving a very brief, actually 2-pager. Yeah, it's 2 pages. 2 pagers for your entire thing, so that you guys don't have to worry about what I didn't understand, what I didn't. And I will also be hyperlinking some of the concepts that are there here. Mac units are like more of EC guys. So if you are a CS guy, I think probably you will not be knowing it. So I'll be putting the links also, so you guys can go and study there. So I know the pain. Amit Mate sir should be knowing the pain of the EC people, because he's also an EC person.
Yeah, no, I actually did a joint. I actually took computer science courses while I was studying masters in EC.
Oh yeah. There are electives.
The pain of both sides. I am aware of the pain of both sides. I think I think we have to marry the EC with the CS to build products. I think there's no way around.
Yes, there's no way.
So you have to talk to your friends who are doing EC, and the CS guys have to talk to the friends. Similar for EC guys, you talk to your CS friends, and but I am also available. I mean, in case people are interested and they want to post questions, my LinkedIn profile is there. You can post a question, or I am sure Vishwas's notes will cover more than you need to ask. But feel free to ask. Yeah.
Yeah, sir. Like I had some questions, like
Sure.
for a very long time, like about the edge computing. Like computer vision has been such a huge ethic workload on the compute engine so far. Like if you take OpenAI, it's coming out with 1 billion parameters, even more than that. Can we inculcate such kind of an hefty algorithm onto an edge compute tomorrow? Like I'm asking you, a mini-me version of that neural network architecture onto an edge computing, like after optimization and everything.
Yeah, no, I think that's where we want to go actually, and I think a lot of it has to come from the need. And so what happens is, once people would love this battery operated robots, right? And these battery operated robots, what you need to do is they need to see, hear, move around, and operate things, right? And to understand and operate things. And so you can imagine the number of AIML models that we'll need on these battery operated devices. And I think that is something which you can easily assume that they will be able to understand all the speech. So they'll have a lot of LSTM or RNN networks. They'll have a bunch of deep neural networks to do CNN type networks to do visual processing, and also they need to have deep reinforcement learning networks to operate things, right? And so all of it has to come together. I mean, so billion would be nothing in a few years' time. I mean, I can imagine, the way yeah, the chip industry is moving, and the kind of neural architectures that are coming up, and in the progress people are making, even in the architecture level of the models, how they and building purpose, custom models. I think this is possible, I feel.
So, like you also mentioned about monocular depth sensing through one of your projects. So, I was thinking of like optical flow has also been one of the problem statements which we are trying to solve in terms of gaze prediction, in terms of action prediction for the self-driving cars. Now, I just want to
Right.
ask, like, such humongous architecture, like it's a kind of an humongous one compared to monocular. Monocular is also a hefty load to the compute, but like I want to
Right.
ask, like, can we really get an optimized optical flow algorithm onto an edge compute tomorrow in such a way that it can predict some more insights on? Like I will say, like Google came out with a project where just by the image of an eye, they could predict many other diseases. Kind of.
Right.
Can we really go to a depth where we can neural network starts giving the insights about the scene which it's seeing or else anything which it's seeing through edge? That's what I'm asking.
Yeah, yeah, no, I think that is possible. I mean, see, today's edge compute, especially Qualcomm Snapdragon, this is public information, can do 21 tera operations, 21 tops of compute. And what you saw in that Resonate 50 was 4 billion. So the thing is, the skill lies in how do we extract the
Extract.
this hardware, right? And I think that's where most of the skill lies in terms of achieving the intelligence, the level of intelligence that you want, right? You have to work with a lot of constraint. I mean, the AI compute is one part of it, but getting the sensor data, doing the processing, it requires really a very seamless software architecture which allows you to do all of that. So I think as people solve problems in different areas, right, sensors, AI compute, and then the model innovations, so these things will start coming together. I am not I'm not worried about it. I think this will happen. I mean, these people are working on it, so it will be there, I think.
Yeah, I know. I know people don't have any questions now because it was a good session, but like I had a lot of thoughts, that's for sure.
That's good. That's good.
No, but like when we see FPGAs, there are DSP slices which come up. There is a section for DSP itself. But like
Right.
on the other side, when we see Snapdragon coming out with its own processor with an extended DSP SDK,
Right.
it's a whole new level of combination of such amount of compute which is running on such kind of an software. When you told about
Right.
software architecture, I was thinking like, how far can DSP be optimized tomorrow? I'm asking you in terms of power, process, and area, because I don't
Right.
see much of black box has been one instance where neural network has been a black box, and even a chip has been a black box to some extent because
Right.
nobody knows what's there inside, but you can somehow configure it, the
Right.
FPGA. Like, how
Right.
can these configurable hardwares be much more optimized, like 1000x roughly? I know it's
Right.
hypothetical, but like, can we optimize it to such an extent that we can really scale up one system to accelerate different kinds of data sets like genomics, proteomics, and all these kinds of
Right.
data sets?
Yeah, I think that's a great goal. But see, you have to see the Moore's law in action, right? I mean, the amount of power that you have on today's smartphones in probably 60s and 70s, that was the supercomputer. And yeah, can you hear me, Vishwas?
Yes, sir, I can hear you.
So I think that yeah, so I think that I feel will happen. And so the problem has to be broken down. As I said, people have to work at different layers of the DNN stack. Some at the very bottom, some at the top layer. Then also there is a software architecture. I think it's not an isolated problem. So people are, the guys who understand the what you said, the power area and the
Process, power
processing,
process
right?
and area.
And so they are working in isolation in terms of like they don't worry about the workload, but they'll just see how they can optimize that. And the guys who are working at the upper layers, they'll say, okay, how can I achieve the same with fewer layers in DNN, irrespective of what can be accelerated. And so when
Yeah.
all of this together, you see the effect, right? That's how most of the technologies evolve, man.
Yeah, sir. I think 6 people were there. 4 people now. Like people come out with questions. I know edge computing is not something that you care about today because you have GPUs running in your laptops. But I'm poor. I need edge computing.
Yeah, I think
Yeah,
it's not a matter yeah, it's just a matter of how much intelligence you want to put in there. I think that's the thing. That's the race. That there's no end to how much intelligence we need, right? I mean, it's a cat and mouse game. Today you
yeah.
have one people figure out how to fool it, then you want to put more, and I think
Yeah,
that's really yeah.
but like, what's the Gmax solution? Like, are you giving out any frameworks or else dev boards like Raspberry Pi is coming out with it? Balena has been coming out with their own boards. Like, are you coming out with any new dev boards that people can really work on these kinds of aspects, like machine learning and deep learning on edge? Like any software also?
Yeah, so no, I think at this point we have become like a AIoT as a service company. So what we have done is we focus on the end-to-end solution, and so we have married artificial intelligence with IoT devices and software as a service. And so
Oh
we kind of interact with the customer who sign up on a portal through the SaaS portal, and then they get these apps on the IoT device, right? But we ourselves don't build the IoT device. We encourage them to use the best in the industry, and these are custom, right? First, because some applications require a different form factor. Like some require, let's say, bullet, some requires edge, some requires a bullet dome or display based. Some of them need board, and so maybe the AI ML is the same. It's same facial recognition, but when it goes in automotive, it's a different form. When it goes in a mall, it's a different form. When it's an office, and so as a startup, we cannot really focus on that part. What we're saying is we know what is good out there in the market. We'll tell you what it is to our customers, and we focus on the AI part of it, right? Like how to really make the AI components that work on the edge, that work on the network, how to combine them to give a better solution than most of the competitors, right? I think that's really has been our philosophy. Now it may change. I mean, maybe few years down the lane, we might be doing
yeah,
boards. If we get
that's true.
bored,
That's true.
make boards.
Yes, that's true. That's true. No, waiting for it, waiting for it. I'm waiting for it. So yeah. No, I think this is the end of the session.
Okay.
If
Yeah.
you
No.
want, you can explain, sir.
No, I think that's about it. I think maybe there's a slide which I wanted to share in terms of the energy, right? I think since you mentioned power compute area, right?
Yeah,
There's one
yeah.
slide. Yeah,
Yes, this is the slide.
yeah. So I think this kind of is the baseline for where most of the edge computations are moving, right? And I just wanted to highlight this is again I got it from a research from MIT paper, but
Yeah,
this
yeah.
relative energy cost, right? 8-bit addition, 16-bit addition, 32-bit addition, floating point, and then these reads, right, from the DDR, from SRAM. And so this should be used as a rule book in terms of when you are implementing a network. Should I use a 8-bit or 16-bit or 32-bit? The answer is clear. Use 8-bit wherever possible, right? Because at the end of the day, if you're doing that, then you'll be able to add more networks, more intelligence on that battery operated device, right? In a smaller area, and then you can reserve other areas for adding, let's say, or processing more sensor data or doing other stuff, right? Because it's AI ML processing is just going to be one kind of processing on that edge device. Yeah, so I think this is about it, man. I think this is something which all practitioners should remember and build or optimize their networks accordingly.
Yeah, sir. At last there's a Praveen Raghuvanshi. I think he's from your side, Gmac.
No, I think I
Praveen,
have. Yeah.
he's from Gmac? No, no. Okay, fine.
No, no,
He's
no, no.
asking he's asking what kind of hardware is recommended for intrusion detection, starting with hardware for prototype and production. Like he's asking like hardware for both the production and the prototype.
Yeah, so my philosophy has been always prototype on the production hardware. So as a startup, you will minimize the time needed.
Yeah, yeah. But
And
like what kind of hardware?
yeah, so I think it depends on intrusion detection. So this intrusion means, let's say, if it's detecting a human being or a person, right? This can be done with any camera today, and so you can do any cameras that have edge AI processing capabilities, and they come in various form factors, like dome, bullet, or display. Yeah. So,
Yes.
question, Praveen. Yeah, I think intrusion detection is one of the simpler problems. You can even, I think, TinyML and Tiny Vision, they also have some kits where you can build this kind of intrusion detection. So, yeah, take a look at that too. Or write an email to me. I'll help you on that in case it's your research project. Just write to me on my LinkedIn profile. Yeah.
Yeah, I think you can put it in the comment section. No, I'll put it in the description section. Sir.
Yeah.
Yeah.
Please.
I'll put it in the description section. I think thank you so much for this amazing webinar on edge computing. I was always thirsty to learn more. So yeah, I did an edge computing workshop at last. Yes. Thank you so much for that.
Yeah, I did it just for your enthusiasm, man. It's 45 minutes of fun when you are around. Yeah.
Yeah. Thank you so much, sir. Thank you so much. I think
Thank
we
you.
are ending the broadcast, people.